In this problem, we have a two-bar system constrained between two walls with an applied force being applied in the middle. And this problem is indeterminate as described in the video for the class, because if we only use equations of equilibrium, we will have more unknown variables than we have equations to describe the resulting forces or the forces that are involved in the system. So we have to bring in some constituent relationships. In other words, bring in information for how the displacement is related to the forces and the spring coefficients. There are two ways to approach these types of problems. One is by using geometric compatibility and equilibrium equations, and the other is using the method of superposition with geometric compatibility and our constituent relationships. So in this example, I'm going to focus on using superposition. And to kind of get started, what we'll envision is removing the right-hand constraint or the right wall from this system and imagining that the force in the middle is applying its force to the right, and we have some displacement delta 1 without the wall there. Now, we realize that this right bar is just along for the ride. So the displacement delta 1 is going to be completely dependent on this force acting in this spring or in this bar on the left. We'll also apply a fictitious force from the right side that would overcome this delta 1. So we have a delta R that is going to be from FR. Now, it's not really fictitious. This is actually the force that we're going to have from the right wall acting on the left. But initially, we're just thinking, oh, what would the force be that allows us to overcome this displacement delta 1? So this means that the delta R and the delta 1 have to be equal to each other, or that delta 1 minus delta R is going to be equal to 0. As I mentioned a second ago, or a few seconds ago, the displacement delta 1 is only going to be due to what's happening in the left bar. And so we can think of the delta 1 as just being the force that's applied in the middle, this force, on this bar, where the right section is along for the ride. Now, what is delta R? Delta R, okay, which is equal to this delta 1 as well, is going to be dependent on this force from the right acting to compress both of these bars. And we know that the bar on the left has spring constant K1 and the bar on the right has spring constant K2. These two bars are in series with each other with this applied force. And so we can figure out what delta R is in terms of the inverse of the summation of the inverses of the individual spring constants. Now, if we perform a little bit of algebra here, we have our equation for geometric compatibility, and we pop in this equation, we pop in this equation, and we are able to solve for FR. Okay, so this FR is the force of the right wall acting on the system. If we want the force on the left side acting on the system, we can go back to external equilibrium on the entire system, where we have our R1, we'll call it, acting, and we can pick a direction, but let's say it's acting to the left. We have our our force, external force acting in the middle, and we have the FR that we just calculated. So we can write out using equation of equilibrium for the forces on this external perspective of the system that the force minus, so this force F, minus FR minus R1 is going to be equal to 0. And R1 is therefore going to be equal to F minus FR. And we know what FR is because we calculated out here using superposition, geometric compatibility, and the constituent relationships, so that we get that R1 is equal to K1 over K1 plus K2 times F. And this result is exactly the same as you will see in the video uh, for the class using geometric compatibility. And if we want, we can also use Colab to solve this problem with numeric values. And once again, we can see if we have a Colab, whoops, what happened, already prepared for us. Let's see here. There we go. And if we go, okay, so if we go to the website, so we have to leave, I'm going backwards. And this is for session 3, MechMat, the Colab, right down here. We click on it, and we're going to go ahead and run the first cell. We only need the import NumPy, and then we can go down to the bottom. And if you want to save your work, you can of course bring this notebook into your own Google Drive and keep it in a directory for your later review. But if you go down to the bottom here, what you'll see is example 3.5, okay, which is determinate loading with values. And you got some screenshots of the algebra and the analysis that we've done so far. So we can plug in various values for K1, K2, and F. And then we can get the resulting forces involved in the problem. So if we run this, that was a control enter on a PC, we get values. Thank you very much. I hope you found this information helpful.